Alright, so this is my demonstration 2. Let me go ahead and just pull up the document real quick. Um, yeah, here it is. So just beginning with the first problem. So I pretty much described U sub for integration as a substitute when you can't integrate it immediately. Then we have to find the inside part of the function, replace it with the variable u, and then find the derivative to cancel out the x variables. And then we can integrate normally and replace the u value in the inside of the function. So for this particular example, the integral of 10x times sine x squared. So pretty much you would take u, which is the inside part, which is x squared. I found the derivative of that, and then replace the dx with the du over 2x since it's the same thing. And then I found that the x is canceled, which would then give me 5, which I moved outside of the integral. And then I could evaluate normally, so I get -5 cosine u. And then at the end, I just replaced u with x squared, and then I added the constant. And then for number 2, u substitution I found will not work for both of the examples, because it doesn't really get rid of the x values. So for example, like when I tried to take the derivative of the inside function and replace it with u, I got 3x squared, which would only cancel one of the x's. And then likewise, when I took the derivative of x and replaced it with u in the second example, which was 10x just sine x, I found that the x's didn't cancel because the derivative was just 1. So we'd pretty much be right back where we started from for that example. And then for number 3, I just said explain integration by parts is utilizing a formula by breaking down two functions that are multiplied by finding derivatives and integrals, and then essentially like crafting the formula. So for this problem, the integral of 10x sine x. So again, you can see I set up the formula there. I identified the u and the v. I found the u to be 10x, and then the derivative of that is just 10. And then I identified dv as sine x, and then the integral of that is just negative cosine x. And then I just pretty much plugged that into the formula. But then the problem that I ran into, or I didn't run into a problem with this one. This was perfectly fine. I ended up getting negative 10x cosine x plus then sine x, and I had to put the plus c out there because it is not doesn't have any boundaries on it. And then for the fourth one, I believe this was the integral of x squared e to the x, and the problem was asking why the integration by parts wouldn't work here. Or it said select the wrong u intentionally. So I selected e to the x as u, and essentially I found that since the derivative of e to the x itself is still e to the x, um, the integral part of the formula for integration by parts is just going to be essentially the same thing. As I said here, the integral is not at all simplified, and integration by parts is needed again. However, since the derivative of e to the x, again, is just e to the x, the problem will be perpetual. So since you are performing the integral on x squared, and given the fact that you have to add 1 to the exponent and to the denominator, it will just keep going since e to the x will always be the same, and you'll never reach a conclusive answer if you were to select e to the x as the u variable. Then number 5, I just described trigonometric substitution as a method for evaluating integrals by using trig identities and manipulating functions. So you kind of had to tinker around with this one a little bit. The problem here was the integral of the square root of x squared plus 16. So immediately right off the bat, I identified this one as the x squared plus a squared formula that we learned in class. So pretty much I wrote x as 4 tan theta, since you have to do a in front of the tangent, and a squared is 16, so it must be 4. And then I found the derivative of that, attached it to the front portion, and then just did some basic sort of manipulation using the trig identities. Here, such as tangent squared plus 1 equals secant squared theta. And then again, I included the derivative going all the way down until I finally ended up at 16 times the integral of secant times secant squared theta d theta. Again, it's just in terms of theta here. I combine that to get secant cube theta. And then I pretty much put this into the final formula here after, or not formula, I guess I should say, after the integration here. And you'll notice that here everything's still in terms of theta, which is fine, but we wanted to pretty much replace this with the x variable. So we have to make a right triangle and then use things such as like SOHCAHTOA, in relation to the angle. So on the right there, you'll see I identified tan theta as x over 4. So right off the bat, I knew that I could fill those in. And then I just did some basic kind of algebra here with the Pythagorean theorem to get x squared plus 16 as the hypotenuse. And then we needed to find secant, and given the basic trig identities, that secant is the inverse of cosine. And given the cosine equals 4 over the square root of x squared plus 16, I was able to flip that over and then get this as the final answer for this one, which is just 16 times 1/2 times what was originally secant theta, but we put that in terms of x, and then this is tangent in terms of x, and then so on. And then obviously the plus c at the end there. And then for the last one, just studying some of the final terms here. I chose to do example 4 from the practice. It was just pretty much calculating work essentially, which is I think it was work equals, I think it was distance times force, I believe. And then we have a basic formula for calculating that. It's just W equals the integral on a boundary f of x times f of x. And so pretty much right off the bat, it identified it required 15 units of force to get from 15 centimeters, or to get the spring from 15 centimeters to 24 centimeters. So pretty much we could just take the difference of that, which would equal 9, and then put that in terms of meters, which is 0.09, and then set it equal to 15. 15 equals 0.09 k using Hooke's law for that one. And again, then we could just solve for k, and we end up getting 166.6 repeating. And then to find the final answer for the work problem, again, we just plug it into our original formula here, and we make the boundaries. The intervals that it was asking for at the beginning of the question, so 15 to 32. And again, we put it in terms of meters here, and then we just take the integral, which ended up giving us approximately this answer right here in terms of units of work that it would take to get the spring from 15 to 32 centimeters. Thank you very much.